Okay, so welcome everybody. I hope everything went smoothly with getting your data and being able to log on. We'll start off slowly so that the people who are joining a little bit late can join us without missing too much. But we are recording now, so if you want to put in your name into the chat so that we can get a record of your attendance, that will be very useful to us. So I hope you're all doing fine. I hope you all had good weeks and good weekends. I'm a little bit tired today. I was saying my daughter woke me up several times last night because she was having bad dreams, so I did not sleep so well. But overall, should be doing okay. Okay, good. So I want to continue with what we were doing with these optimization problems because they are really quite important. So I want to make sure that we do enough examples of them so that people really see a variety of these different optimization problems. And then in the second half of today, we'll talk about graphing and calculus and what calculus and graphing have in common and, what calculus can tell us about how we graph things. Okay. So yeah, welcome everybody again. Remember to put in your name. And for this week, I just want to start with a little review for this general strategy we have for optimization problems. So this general strategy over here, which we had a slide for last time, I'm just repeating it, is that how do we solve an optimization problem? We're trying to maximize or minimize something. And if you want to translate that into calculus, into math, then you have to interpret whatever situation you're in as maximizing or minimizing some function on some domain. Okay? And to do this, this may require several steps. So the first one is to understand the problem. What are you trying to maximize or minimize? And what are the constraints? Your inputs may have some constraints. The second thing is you may need to draw a diagram or introduce notation for the relevant quantities. Step 3 is this quantity Q that you want to maximize or minimize, you need to write it in terms of an equation in terms of the other quantities in the problem. And then maybe you have a whole bunch of quantities, 2 or 3 different things that are going into Q. If you want to do optimization the way we've been doing it, you need to convert everything so that you only have one input, okay? So that everything is a function of just one variable. So that's this quantity Q. You need to write it so that it's a function of only one variable on a particular domain. So this is often a very important step that you want to have. And then lastly, now you've gotten it so you have some function that's a function of one variable on a domain, and then we know how to maximize or minimize the relevant function, right? What we need to do is find the critical points and check them, and also endpoints if applicable. Okay, so this is what you're doing when you're maximizing the relevant function on your domain. Okay. Okay, so let's go over some of these problems on the homework. So number 1 is relatively straightforward, to just find the critical numbers of the function t to the fourth plus t cubed plus t squared plus 1. And before we do this, let me just recall, remember that a is a critical number of some function f. Well, in this case, our variable is t, so I'll call it f of t, if f prime of a equals 0 or f prime of a does not exist. Okay, so to find the critical numbers of this function, does somebody want to do it for us?
Yes.
Yes, James.
Yeah, you have to find a quadratic equation.
Mm-hmm.
Yeah. T will be equal to D plus or minus 1.
D plus or minus Well, so what do we have to, if we're trying to find these critical numbers, what do we have to first calculate?
The derivative.
Right. Great. So what is the derivative? So we have to do d dt of t to the fourth
Yeah.
plus t cubed plus t squared plus 1. So what is that?
It's, it will be equal to 0.
Oh, we want to set this equal to 0, right?
Yeah. Yeah.
Okay. So what does this left-hand side become then when we take this derivative?
Robert?
You have to find.
Yeah.
Sorry, James, other James Caselli
Yeah.
question?
The
Yeah.
derivative will be like uh
Oh, let's let James Va finish, right? Because he was in the middle of doing it. James Va, do you want to finish? Or you're muted. Or okay, if not, uh James Caselli, do you want to go finish? Oh no, James
Yes.
Va,
can I
there you
try?
are. Sorry, James Va. Sorry. Yeah,
Yeah, you have to find the quadratic. I'm
right.
sorry for the poor network.
Okay, no worries. But so we need to take the
Yeah.
derivative here. So what's the derivative of this function?
It will be T.
Mm-hmm.
Hello?
Yep. T. Mm-hmm. T.
T is equal minus 3. T equal minus 3.
Okay, I don't want the answer yet, right? I mean, it's too early to skip to the answer here. Let's try to do
Or
it step by step, right? So what we have to set this derivative equal to 0. So that means we have to take the derivative here, right? So what is the what is the derivative first of t to the fourth plus t cubed plus t squared plus 1?
Yes, can I try?
Yes, Princeton? Yep.
Yes, and we're taking the derivative of t raised to the 4 power will be 4 t raised to the third power
Mm-hmm.
plus 3t raised to the second power
Mm-hmm.
plus 1.
Careful. What's the t squared here? What does that become?
T squared is 2t.
Exactly. Right. So that's exactly right. Equals 0 because the 1 disappears.
Yeah.
Okay, great. So we want to solve this now. Okay, so how do we solve this equation?
by finding a quadratic.
Great. So yeah, so we pull out a t, right? And this is t times 4t squared plus 3t plus 2 is equal to 0. And then yes, James, so for the quadratic formula, remember we
Yeah.
recall minus b plus or minus the square root of b squared minus 4ac over 2a. So what do we get by the quadratic formula? We get, of course, either t equals 0 or, yeah. So what does the quadratic formula give us here?
So T now will be equal to
Okay. So let's,
hello?
yes, hello?
Andrew?
Yes, I'm here.
T will be equal to negative 3
Mm-hmm.
plus or minus
Mm-hmm.
or square.
Yeah.
3 square
Yeah.
minus
Mm-hmm.
4 times 4
Okay.
times 2
Four
equals
times four
2
times two.
times 4.
Yeah. Great. So 4 times 2. Great. All of this divided by um all of this divided by 8, right?
Yes.
Right.
Yes.
Yes. And now what happens under the square root here? What kind of number is this under the square root?
Discriminant.
Right. But in this case, right, we've got 9 minus 32, right?
Yes.
So this is negative, right? It's a negative number, right? And so that means, right, that these solutions here are not real solutions. They don't count for our
Yeah.
critical numbers. They're imaginary. So in fact, since in
Yeah. They're
calculus
not
right
real.
now we deal with the real numbers, right? So
Yes.
right. So in the answer, we get the only critical number here actually is t equals 0,
True.
right?
True.
That's the only choice. And let me show you what this looks like in the graph. So I'm going to go bring up Desmos, which is this graphing. So let me share my screen to show you the graph. Um, where are we here? So if we use the graphing calculator here on desmos.com, then if I draw this, I do, y equals t to the fourth plus t, sorry, plus t cubed plus t squared plus 1. What do you see here? You have a critical point right here at t equals 0. This is going to be a local minimum, right? It's a critical point with a flat tangent line, and that's it. It actually looks kind of like a parabola, although it's not exactly a parabola, but it kind of looks like a parabola. And if you zoom out, you see that's just what it is. It doesn't have any other critical points. There's nowhere else where you have a horizontal tangent line or a vertical tangent line or no tangent line. You have just this one point. Okay, so even though it looks like there might be three solutions, there's actually just this one solution. And this is the critical point right here at t equals 0. We're using the t instead of x, but I mean, the letter doesn't really matter. It could be x. So you have t equals 0 over here, and it turns out that this is a local minimum. Okay, so and it's the only one. So we can see from the graph that there's no other critical points. Okay, let me reshare on my iPad. Reshare here. Okay. Okay. Good. Okay. So any questions about this problem?
So, yes.
Yes, Princeton?
So what made this to be a critical problem is because it ain't negative or because there's no perfect square root.
Oh, right. Yeah. So there's negative, right. So maybe I should say this negative. So no real square root. And so that means these solutions, so these are not real solutions. And so when I'm looking for critical numbers, it's implicit that we only want the real solutions because we're looking for real solutions to whatever optimization problem we want to do. So these things, I mean, technically, they're what are called complex numbers. They're complex solutions, but they don't have any bearing on any actual optimization of anything this problem might want to model. Okay, so we're only interested in the real solutions. And in this case, that's going to be only t equals 0. And these are not real because they involve taking a square root of a negative number, which you can't do in the real numbers. Okay,
Okay, that's good.
good. Okay, other questions?
Thank you.
Thanks for that one. Okay. Okay, let's move on. Okay, so exercise number 2. If a and b are positive numbers, find the maximum value of this function f of x equals x to the a times 1 minus x to the b on the interval 0, 1. So in this case, we'll have to use the general power rule. Remember, the power rule, that just means it works with any number in the exponent. It doesn't need to be an integer. And oh, actually, I guess this maybe this exercise was not good to assign yet because this actually relies on the chain rule. So maybe it's better to come back to this one after we do the chain rule next week. So let's actually skip this for now. I'm going to skip for now. As this really, requires the chain rule. Okay, which we haven't taught yet, and I will be teaching it next week. So why don't we skip this for now, and we're going to do this next week. Okay, so sorry about that. We'll skip this exercise and we'll do it next week. Okay, good. So let's skip to exercise 3. Okay, so this is a good problem. This is a fun problem, and it hits on a lot of the ideas with these optimization problems. So a rectangular storage container with an open top is to have volume 10 cubic meters. The length of its base is twice its width, and the material for the base costs $10 per square meter, and material for the sides costs $6 per square meter. Find the cost of the materials for the cheapest such container, and the hint is to try to express the cost of materials completely in terms of the width of the container. Okay? So if we go back to our strategy, step 1 is to understand the problem, but 2 is to draw a diagram, right? So maybe we should think about this. Well, we understand the problem. We know what the volume has to be, and we want to build it as cheaply as possible. And our diagram is going to look something like this. We're going to have a box with an open top. So we can draw our box that looks like this, and it's got an open top, so maybe I should really fill in these sides over here. But I'm not going to fill in the top because the top is open. We're not building the top of the box. Okay, so imagine you're building a crate or something like that. So this is our box that we're trying to build. And I'll put the back also. Okay, so this is our box, and since we have a diagram, it's good to label things, right? So we have that the what do I have? The length of its base is twice its width. Okay, so this over here is going to be the length L, and this is going to be the width W, and this is going to be the height H. And what we know as a constraint is that the volume V is equal to 10 cubic meters. Okay. And then what do we know in terms of we have all of these possible inputs? We have the length and the width and the height, but they're constrained in several ways. So what equations do we know that relate the length, the width, the height, and the volume? Well, first we have an equation for the volume, right? We know, right, that the length times the width times the height.
Hello?
Yes,
Hello?
hello, James. James, yep.
Yeah. We multiply the length by the weight
Mm-hmm.
by the
Yep. And that has to give us
10.
10. Great. So this is constraint number 1. What's constraint number 2? That's also in the problem.
Center volume is 10
Mm-hmm.
meters square.
Yeah, cubed.
Here we say two times
Mm-hmm.
the length.
Well, 2 times the length. Sorry, the length is twice the width. So
Oh,
how do we
okay.
write that as an equation?
Okay, 2 times the weight.
Right.
2 times all raised to the 2
Okay. Well,
times the length by the
let's just
10.
keep it simple for the beginning. Let's just write. So the
Yeah.
length is 2 times the width, right? So let's just write 2W equals L, right? These are our two different constraints. I think what you're doing is combining them, right?
Yeah. Yes.
So okay, so let's combine. What do we get? Yeah. I mean,
Yeah,
we yeah. hmm
we have 5
Yeah.
over the weight or square.
Right. So let me just substitute. We'll do that in steps. I have two length is two width. So what we get is 2W times H equals 10, right? This is our length over here. And this then tells us that 2W squared H equals 10. And this tells us that W squared H equals 5. And then, right, if we want to write everything in terms of the width, this gives us that H is equal to 5 divided by W squared. Okay, great. So just doing it in a few steps. Right, so this is good. So we have that now anything involving the length we can write in terms of the width. L is 2W. And anything involving the height we can also write in terms of the width. It's 5 over W squared. Okay, so now what is the quantity we want to maximize or minimize? It's the cost, right? We want to minimize the cost. The cost to build. And so we have to write what is the cost to build this box? And we'll start by writing it in terms of the length, the width, and the height, and then we'll convert it completely so that it's just a function of the width, because we need to convert it to one variable in order to be able to use our calculus technique to solve it. Okay? So first, what's our equation for the cost? Well, this box has 5 sides, right? It's got a bottom and it's got 4 sides on the side. So we need to know what is the cost of making the bottom and what is the cost of making the 4 sides, right? So let's first talk about the bottom. So if the bottom costs 10, the base, that costs $10 per square meter. So what is that in terms of our variables? How do we write the cost of the base? Let's have a little basic geometry here.
Hello?
Hello, yes?
We need to find a derivative.
Well, we don't need any derivatives yet. First, we're just modeling. There's no derivatives yet, right? I'm trying to ask
The
just what
minimum,
is the function for the cost? Yeah.
yeah,
Yes, James?
we have to solve for the weight.
Well, I mean,
Hello?
we already did that, right? We already wrote 2W equals L and H equals 5 over W squared. So we've solved for everything in terms of the width. What I want to do right now is write down what is an expression for the cost of the box. And to begin
Okay,
with, that can involve L, W, and H altogether. But after we write it down like that, we'll convert it to something that only involves W.
okay.
Yeah. So, but
The
what's the
cost,
first expression for the cost? Yeah.
the cost will be equal to
hmm
the volume
Mm,
time.
yeah. The
Hello?
volume, yes, the volume times.
Uh, parenthesis open.
hmm
The weight time, 2 times the weight again.
I'm sorry. I'm getting confused. The cost should be calculated in terms of this information given in the problem. It's $10 per square meter for the base and $6 per square meter for the sides, right? So it should be something involving 10 and 6 and something about the surface area of this box, right?
Yeah,
Right.
yeah.
So it shouldn't really involve volume at all. Um,
Okay,
right. So let's start with the base, right? So how much does it cost to build a box? It costs a certain amount to build the base, and it costs some more to build the sides, right? And you have to build the whole thing. So the base costs $10 per square meter, right? So $10 per square meter for the base. So what does that mean? So if that's how much the material costs, then what is the total cost to build this base? So what is the size of the base of the box based on this diagram that we drew? What's the size of the base?
looking at the, hello? Andrew?
Oh, James, yep.
Yeah.
Yep.
I looking at the total cost to be the total minimum cost
Not the total minimal
to be.
cost. The total cost as
Oh,
a function of L, W, and H. Nobody could calculate the total minimal cost in their head from this problem, right? You need to first write an expression in terms of your variables for the cost. So it's going to be a variable expression involving L, W, and H, which we're then going to use to calculate the minimal cost.
will there be the semi circle of lap box?
Circles, and it's not, and there's no circles. This is just a rectangular box, right? It's a rectangular box.
Hello?
Everything's a right angle. Yeah.
Is that what?
Hello. Yes, Robert.
Yeah, I think to find the cost, yeah, the question says the material for the base cost $10 per square meter.
Right.
I think square meter is the unit used in finding area, so the base should be the length times the width.
Exactly. So we have the length times the width times 10, right? This is the base, the cost of building the base,
Sure.
right? Great. So do you want to do the sides also? Robert, would you like to do the sides?
Yeah, the question says is size cost $6 per square meter.
Mhm.
So the size would be the width times the height times 6 as well.
Right. So you have one side here is the width times the height, right? So we're going to get 6 times width times height. And then this side over here is also the width times the height, right? It's the opposite side. It's the same area. So we're going to get
Sure.
another 6 width height. But what about this side over here? This side in the front. What's its size?
The side in the front will be the height times the length.
Exactly, right? So we're going to get 6 times the length. Sorry, not, yeah, 6 times the length times the height. And then lastly, the side in the back is the same, right? So we have 6 times the length times the height. So this is the cost. And if we want to simplify it, we can write this as 10 LW plus 12 WH plus 12 LH, right? So this is the intermediate step. This is what I'm looking for, right? We have an expression which we're going to try to minimize. This is the total cost of building the box. This is 10 times the length times the width plus 12 times the width times the height plus 12 times the length times the height. This is the cost of building the base and the left and the right side and the front and the back side. So eventually we're going to convert this all to W and use calculus to minimize it. But before we do that, I want to make sure that everybody understands why this is the expression that gives us the cost. Okay, because this is very important to know that we have an expression for the cost to work with. If we can't write down the cost as a variable expression, then we can't work with it to minimize it. Okay, so are there any questions of how we derive this formula here? 10 LW plus 12 WH plus 12 LH. Okay, that's all right. Okay, let me just rewrite this on another page. So the cost, so we have just cost. I'm just going to copy that down. Cost is equal to 10 LW plus 12 LH plus 12 WH. And then we also have from the previous page, we have ways of writing the length and the height in terms of the width. So here we have that the length is equal to 2 times the width, and the height is equal to 5 divided by the square of the width. Okay, so we derived both of these. So now what we're going to do is rewrite the cost in terms of only W, in terms of only the width. Okay. So what do we have here, right? So, well, L is 2W. So cost is equal to 10 times 2W times W plus 12 times 2W times H, which is 5 over W squared, and then plus 12 times W times H, which is 5 over W squared, right? Over here, all that I did was rewrite the length, and then this is the length, this is the height, and this is the height again. All right, we just rewrote our expression so that everything's in terms of W, right? And if we simplify this, this becomes 20W squared plus 12 times 2 times 5 is, this simplifies to 120 divided by W, and this becomes over here 60 divided by W, which is equal to 20W squared plus 180 divided by W. Okay. Okay, is everybody with me so far? Okay, so we've done all of this work to finally get cost, which is a function of only one variable. It's a function of just W. Okay? So the cost is this function of W, right? We had to do a lot to get to this point, right? We had to use the volume. We had to use this information about the constraints that the length times the width times the height is equal to the volume, and the length is equal to 2 times the width. We had to combine these to get expressions for all of our other quantities in terms of W. And then we had to actually write down the cost function using a little bit of geometry to say what is, what is our actual function that's going to give us the cost. Okay. So, but now we finally have cost equals 20W squared plus 180 over W. So to minimize this, now we can take the derivative and use and find the critical points, and that's where we're going to have possibilities of minimum. Okay, so now take the derivative. And
Hello.
equal to 0. Yes, Enoch.
Yeah, that boss. How you doing?
Hi, good. How are you?
Yeah, I'm okay. Actually, my phone gave me a time. The phone got the battery down, so I'm just joining. I just use someone phone and logging my information to just join the class.
Okay. Okay, thanks for
Yeah.
joining.
So, yeah.
Okay, great. So what happens when we take this derivative? Well, maybe I should just rewrite this. Another way to write this is 20W squared. Instead of 180 over W, I'll write it as 180 times W to the minus 1, just because this is easier for calculus, right? We want to do derivatives using the power rule. It's easier if we can write this as something involving the power rule. Okay? Okay, so what do we get when we take the derivative here? 20W squared becomes 40 times W, and 180 times W to the minus 1 becomes minus 180 times W to the minus 2. And we have to set this equal to 0, right? Power rule, we bring down the minus 1, and it becomes a minus 2. So now I'll just solve this. We can have 40W equals 180 W to the negative 2. Move it to the other side. Now maybe I'll multiply both sides by W to the minus 2. Sorry, by W to the 2. So we're going to get 40W cubed equals 180, right? I multiplied both sides by W squared. And then we get this gives us that W cubed equals 180 over 40, or in other words, equals 9 halves when we reduce it. And so W is going to be a cube root of 9 halves, which is calculator, so cube root of 9.
4.5.
So 9 halves is 4.5. So 4.5 raised to the 1/3 is going to be 4.5 raised to the 1/3 is, this should be about 1.65. Yeah, okay.
1.65.
1.65, right? So this is the width. Now, did we answer the question? We've got to go back and look. Well, it says, find the cost of the materials for the cheapest such container. Find the cost. So we're not done just because we found the width. What we actually need to do is find the cost, right? But the good news is we have a formula for the cost in terms of the width. The cost is 20 times the square of the width plus 180 over the width, right? So I'm just going to rewrite this. We'll take one more page. So we have that the width is approximately equal to 1.65. And so the cost is equal to 20 times the square of the width plus 180 divided by the width. And so this is going to turn out to be, I'll just plug it in. So 20 times 1.65 squared plus 180 divided by 1.65. So this is going to be roughly $163.54. Okay. Yeah, I think this is what we have. Okay, so this should be about $163.54. Okay, so that's how much it costs to build one of these boxes if you do it in the cheapest possible way, which is to make it so that the width is 1.65, and if we wanted to, we could figure out the other parts also, right? If the width is 1.65, the length is going to be twice that, so that's about 3.3, and the height is also going to be 5 divided by the square of 1.65, which is probably about 2. You can figure it out on a calculator if you want. Well, the point is this box is going to look pretty, like the sides are all going to be kind of similar to each other. It's going to look about as close to a cube as it can. That's what the calculus is telling us. Okay? So the only calculus we're actually doing here is taking a derivative and setting it equal to 0, right? The calculus is not complicated. The hard part of a problem like this is the modeling, right? Is to do the modeling correctly so that you actually can figure out what is the function that governs the cost and how can you write that function in terms of only one variable. Once you've done that, then the calculus is just this. And the calculus just take the derivative, set it equal to 0. It's not a hard equation. But the harder part is to come up with the correct cost function. Okay, and with a lot of these optimization problems, that's what happens. The hard part is not the calculus. It's not taking the derivative and setting it equal to 0. The hard part is actually, setting the problem up so that you have the right function to take the derivative of. Okay. So any questions on this?
Yeah, that all works.
Robert?
Yeah, I'm trying to understand the reason why we set the cost equal to 0 when trying to find a derivative.
We don't set the cost equal to 0. We set the derivative of the cost equal to 0, right? So this is the cost right here. We never set this equal to 0, right? What we do is we take the derivative and we set that equal to 0. And the reason is because the cost is this function that we want to maximize or minimize, and we know that where that minimum happens is at the lowest possible cost. Wherever that minimum or maximum can happen is at a critical point, right? Which means it can only happen where the derivative is equal to 0, right? Kind of visually, what happens if we look at our cost function, if this is our width and this is our cost, then we're going to have at 1.65, this is going to have a minimum. So basically, the smaller we make the width, the cost is probably going to go up. And then over here, we have a minimum. And then as the width gets bigger, the cost goes up also. So the graph probably looks something like this. And the place where the cost has a minimum is exactly where the tangent line is horizontal. And since the tangent line is horizontal, what that means is that the derivative of the cost with respect to width, so we can write it C prime of W, is equal to 0 over here.
All right, I understand. So that is a local extrema, right?
Exactly. And in this case, it's the only one, so it's also the global minimum, because it's the only critical point.
Thank you.
You're welcome. Yeah, so we're never setting the cost equal to 0. In fact, the cost never will be 0. If you tried to set this equal to 0, you wouldn't get a solution, or you wouldn't get a meaningful solution. You wouldn't get a positive solution. But if you set the derivative equal to 0, that's telling you exactly where you have a local minimum. It's telling you where you have horizontal tangent, which is going to be some sort of local minimum or maximum. And to James's question, yes, the minimum cost is also the cheapest cost. It's the same thing. All right. Any other question? Okay, good. So I really like this problem. So if you're able to go back over the notes or watch the video, if any of this didn't make sense, then this is really a good problem to study, right? Because this problem takes into account all of the issues that show up for these optimizations. You've got a whole bunch of variables. You've got to rewrite it as one. You've got to write a formula for what you want to maximize or minimize, and then you have to do the calculus. Okay. Yes. The minimum cost could also be considered the best price. Yeah. Best price, cheapest cost, minimum cost. It all means the same thing, right? The point is you want a container that's going to hold 10 cubic meters and you want to build it as cheaply as possible. And so in this case, this is going to be the way to do that. Okay. All right. So let's do one more exercise. This is one that we skipped last week, but I drew a diagram. So a fence 8 feet tall runs parallel to a tall building at a distance 4 feet from the building. Okay, so this is 4 over here. The fence is, oh, sorry, not 4. Sorry, this is the building. Let's call this the building. And we have a fence that's 8 feet tall. Put the 8 over here. And then the distance between the fence and the building is 4 feet. Okay, so we write that over here. And so the question is, what is the length of the shortest ladder that will reach from the ground over the fence to the wall of the building? So I'll draw the ladder in red. So let's say that we have a ladder like this. Right? So we have a ladder like this. And we want to know how short can the ladder be. And so the hint that I gave you is let X be this length over here. So basically the height on the building that the ladder hits. Okay, we're going to let this be X. Okay, maybe I'll rewrite it over here. So if we call this X, okay, so we let X equal the height on building where the ladder touches. Okay, that doesn't mean it's the height of the building. It's just how high on the building the ladder touches, right? And we're assuming these buildings are straight and the fence is straight. Everything's a right angle here, okay? So yeah, we will use the Pythagorean theorem, but we're not there yet, right? So our task really is we're going to, write down the length of the ladder in terms of X. Okay. So again, this is a calculus problem. We're going to be maximizing or minimizing something, but the calculus is not the hard part in this problem. The hard part is figuring out the geometry, the stuff that's closer to the curriculum, figuring out the geometry so that we can actually write down an expression for how long this hypotenuse is here. And the answer is yes, we will use the Pythagorean theorem. But if we want to use the Pythagorean theorem, where we have this X, we have this 8, we have this 4, we're going to have to figure this out too, right? We're going to need to figure out there's some other length Y. over here. We're going to need to know. So the question is, can we write down y in terms of x? Right? So, I mean, the length of the ladder is certainly, so let me call the length of the ladder L. The length of the ladder is L. So by the Pythagorean theorem, we have that L squared is equal to x squared plus 4 plus y squared. Right? That's fine. And so in particular, I won't write it down here, but L is going to be the square root of x squared plus 4 plus y squared. Okay, so that's an expression for L. But the problem is that involves both x and y. And when we're trying to do our optimization, we need to make sure that the thing we're trying to optimize is in terms of only one variable, not in terms of both. So, right, we need to calculate not just approximately the base, we want to know kind of exactly what the base is, and we want to be able to convert y to some function of x. Y should be something that involves x. And we're going to need to use geometry to do that. So does anybody know how to set up an equation that will allow us to solve for y in terms of x? And my hint is, look at these two triangles over here. This triangle, the small right triangle, and then the big right triangle, they share, their angles are all the same, right? So we have a word for what the two triangles like that are called. So what do we have for this smaller triangle and this bigger triangle? What are they, what's their relationship to each other? What's that called? Robert?
I can say if the angles are equal, then some way they might be congruent.
Well, they're not congruent because they don't have the same length sides, right? One is bigger than the other. But there's something, if it's weaker than congruent, they have the same angles, but not the same sides. That's called.
So can we say twice of the smaller triangle?
Similar
to the bigger?
Right. They're similar triangles. Exactly. They're not congruent, but they're similar, right? They have the same angles, but not the same sides. Okay, so these are similar triangles. And when you have similar triangles, you can write down equations involving the ratios of their sides, right? So this is something that we did. Last year for those who were involved in the geometry trigonometry part of the curriculum last year. But similar triangles. Let me just redraw the diagram on another page. So the diagram here is this. We have 8, 4, and x and y. And so, and this over here is L, but I won't even label L. So similar triangles, fact, right? So similar triangles have a common ratio of their corresponding sides. Okay? So in this case, what that tells us is that, maybe I'll draw this triangle in red. The red triangle is similar to the blue triangle. Whereas in blue, this goes the whole way. Right? So for instance, what this tells us is that if I take 8 over y, that's the same thing as x over y plus 4, right? Or another way of saying that would be ratio of their corresponding sides. So the 8 corresponds to the x here. So we would get 8 over x, and that's equal to, well, this side we have y, and the corresponding side in the big triangle is y plus 4. So we would get 8 over x equals y over y plus 4, right? I mean, what's really going on here is that this is a height of one triangle, and this is a height of the other triangle. So the ratio of the two heights is the same as the ratio of the two bases. So this is the base of one triangle, and this is the base of the other triangle, right? So now solving, we can cross multiply to solve this, right? So this tells us that 8 times y plus 4 equals x times y, or 8y plus 32 equals x times y. Remember, we're trying to solve for y in terms of x, so we want to get all the y's on one side. So this tells us that 8y minus xy is equal to 32, which also tells us that y times 8 minus x is equal to 32. And this tells us that y is equal to 32 divided by 8 minus x. Okay.
Yeah, that over.
Yes, Robert.
Yeah.
Mm-hmm.
Concerning what you just did, I
Yeah.
think we can also use trigonometry to set up the x and y.
Yeah, that'll
Like
probably
if we
work.
are to take the base angle,
Mhm.
use the tangent function, I think we can set up equation between the both of them.
Right. So for instance, that's another way of deriving this this equation, right? So if we took this angle as theta, then applying it to the red triangle, the tangent of theta would be 8 over y. And the tangent of theta in the big triangle would be x over y plus 4. So in that case, you would get, you could also get, in that case, 8 over y equals x over y plus 4, which is the same equation. I mean, this equation is the same as this equation, right? You just switch the y and the x's. It's the same on the cross multiply, right? So you could do this in that case without using similar triangles. You could say that both of these are equal to tangent of theta. So they have to be equal to each other.
Sure.
Robert? Yeah, so that works also. If you want to use trigonometry, that's fine. If you want to use similar triangles, that's also fine. They both give you the same equation.
Hello?
Hello, yeah, Enoch?
Yeah, with this method, can I also use trigonometry to obtain a same answer to you as well?
Yeah. I mean, that's what Robert said, right? You can do trigonometry in order to solve for y in terms of x.
Okay.
Yeah, so that works. So the point here is that y is equal to 32 over 8 minus x. Okay, so let's recall, what do we have? We're trying to find the length of a ladder, right? What's the shortest ladder that's going to go all the way? So in order to do that, we wrote that the length squared is equal to x squared plus 4 plus y squared. Okay? So the goal is to get everything in terms of only x. So instead of 4 plus y, we'll substitute our new expression for y. Okay, so maybe I'll do that over here. So since the length squared equals x squared plus 4 plus y squared, we have now that the length squared is equal to x squared plus, so what is this? 4 plus 32 over 8 minus x squared, right? Yeah, so this is what we should have. Okay, I want to make sure I did all my algebra correctly here, but I think it is 8y plus 32 equals xy, 8y minus, oh no, sorry, this is negative 32. Sorry, I made a mistake. This should be negative 32, this is negative 32, this is negative 32. So another way of doing that is that's 32 over x minus 8. So let me write that instead. It's x minus 8, not 8 minus x. Okay. That's actually better because what happens when I simplify this, this is x squared plus, if I want a common denominator, 4 over, if I want to get a common denominator of x minus 8, this would be 4 times x minus 8 over x minus 8 plus 32 over x minus 8 squared. And then when I combine these, this is x squared plus, well, this becomes 4x minus 32 plus 32 over x minus 8 squared. And so that's actually a bit nicer. So it's x squared plus 4x over x minus 8 squared. Or in other words, that's x squared plus 16x squared divided by x squared minus 16x plus 64. Okay, so this is the function that we want to minimize. Okay, or at least this is what L actually is the square root of this. Okay, so I want to drive home that we have not done any calculus yet at all. Okay, all that we've been doing is algebra. We're trying to get an expression for this length that we want to minimize. We're trying to get this expression in terms of what in terms of x, in terms of only x. And we knew by the Pythagorean theorem we could get it in terms of x and y, but then we had to use these similar triangles in order to end up with an expression that involves only x. Okay? So are there any questions so far as to how we got to this? This problem may take a long time to do, but it's worth it. It's really, even if we don't get to do much curve sketching today, the optimization stuff is more important. So I want to make sure that we can go through every step of the problem and not have to rush it. Okay, good. So let me recopy this. These optimization problems can be long, right? They can take a number of pages. So what we have here is L squared is equal to x squared plus 16x squared divided by x squared minus 16x plus 64. Okay, this is the question. Right. By the way, yeah, I guess we could do the entire problem in terms of trigonometry if we wanted to. We could do the entire problem in terms of theta instead of in terms of x. Would that be easier? Maybe. Yeah, probably not that much easier. Probably ends up being the same. But let's keep it in terms of only polynomials. Okay. So now we want to minimize L. Right? We're trying to minimize the length. And we saw a similar problem like this a week ago, or it was maybe a while before that. Is that the x that minimizes L is the same x that minimizes L squared. Okay, right? Because if you can make L squared as small as possible, you're also making L as small as possible, right? The smallest value for the square is the same as the smallest value for the number. The values might not be the same, but the x that makes this as small as possible is the same x that's going to make its square root as small as possible. And so the good news is that minimizing this is easier than minimizing the square root of this, because the square root of this does not have a nice simplification. The square root of this does not have a very nice simplification, which means that it's right, which means that the square root of this thing is not going to be easy to take the derivative of, because derivatives involving square roots use the chain rule, which we don't know yet. Okay? So instead of having to take a square root at all, we can just find the x that minimizes L squared. So we just find the x that minimizes L squared. That's good enough. Or what is L squared from this expression? It's x squared plus 16x squared divided by x squared minus 16x plus 64. Okay. Okay. So what do we do here? So now we're ready for the calculus. Now we're ready to take a derivative and set it equal to 0, right? That's how we minimize things. So after all of this setup, the similar triangles or trigonometry, however you want to do it, writing an expression for the length, making all sorts of substitutions and getting it so that the quantity you want to minimize is in terms of one variable. After you've done all of that, now you're ready to do calculus. Okay, so now we're ready to take the derivative and set it equal to 0. Okay, so what happens when we do this? We get, so the first part, we just get 2x, and then plus, and now this derivative is a little bit annoying, right? Because we have to use the chain rule, right? Not the chain rule, we have to use the quotient rule. So if we recall the quotient rule, remember when you're taking a derivative of a fraction that's of the form g over h, then the derivative is equal to h times g prime minus g times h prime over h squared. This is the formula that we had. This is the quotient rule. Okay, so in this case, we're going to get the bottom times the derivative of the top. So x squared minus 16x plus 64 times the derivative of the top, that's 32x, minus the top 16x squared times the derivative of the bottom. So that's going to be 2x minus 16, all divided by x squared minus 16x plus 64. Okay, so it's not the nicest expression, but it will simplify a little bit. Okay.
I think you should square the denominator, Dado.
Oh, square the denominator. Yes, thank you. Thank you. Squared. Okay. All right, so this is not the nicest expression, but it will simplify. So let's simplify this a little bit. This is 2x plus, we'll keep the numerator as it is for now. Right, so sorry, we want to set this equal to 0. And so that's the same thing as saying 2x. Let's simplify the numerator. I'm going to multiply through 32x by everything here. So I'm going to get 32x cubed minus 32 times 16 is 512. So minus 512x squared. And then plus 32 times 64 is 2048 x. And then minus 16x squared times 2x, that's going to be minus 32x cubed. And then 16x squared times 16 is 256x squared. So plus 256x squared. But the good news here is we see already the 32x cubed and the 32x cubed cancel each other out. And so this is 2x plus, then we have 256x cubed, x squared minus 512x squared. It's going to be minus 256x squared. So we're going to get 2048x minus 256x squared. All of this divided by x squared minus 16x plus 64 squared. Now this is getting a little bit more complicated than I had expected. I didn't work it out in advance, so I probably should have. Okay, so the question is, what's going to happen? Well, you know, sometimes you just have to. It doesn't look so nice. You just have to carry through. All right. So let's see what we get when we carry this through. Okay. Probably we'll take another page of algebra. Okay. So we want this to be equal to 0. We want this to be equal to 0. Okay. So let's keep carrying it through. Okay. So I'm going to just copy this onto the next page. Okay. So we have 2x plus 2048x minus 256x squared divided by x squared minus 16x plus 64 squared equals 0. So let's get a common denominator. So I'm going to get 2x times x squared minus 16x plus 64 squared plus 2048x minus 256x squared. So this will be over x squared minus 16x plus 64 squared. And this will be over x squared minus 16x plus 64 squared. This will be equal to 0. Let me just erase this plus and put it over here instead. Okay, just getting a common denominator. But now the good thing is we've got a 0 over here, so we can just eliminate the denominator, right? So this gives us 2x times x squared minus 16x plus 64 squared plus 2048x minus 256x squared. This is all just equal to 0, right? We can just eliminate the denominator because I can multiply both sides by this denominator and the right side will still be 0. Okay, so, this is good. So we now have a factor of 2x that we can divide by. So we're going to have x equals 0, but we can pull that out if we want. So this is going to be 2x times x squared minus 16x plus 64 squared. And then plus, what happens if we pull a factor of 2x out here? This over here, you could write it as 2x times 1024x minus 128. So 1024 minus 128x, right? So if I pull out the 2x, this is going to give me 1024 minus 128x. Okay, so fine. That's what we have so far. And now what do we have here? This is 2x, and now we just have to square this. I mean, so the algebra gets pretty terrible here, but it's just algebra. Okay? So squaring a trinomial, by the way, this is a formula that you may or may not know, but you should know it. If you have a plus b plus c squared, that's equal to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. Okay? This is a good formula to know. It's just like a plus b squared, but you add in a c, so you're going to get a c squared, and then you get 2 times all of the pairs of terms that you can make. So this is going to be the worst it gets, and then I promise it will get better. So this is going to be x to the 4th plus 256x squared plus 4096, that's 64 squared. And then we're going to get minus this, so minus 16, or 2 times that, so minus 32x cubed. And here we have the x squared and the 64, so minus 128x squared. And then lastly, we have the 16 and the 64. That product is 1024. So it's going to be minus 2048x. And then also, plus 1024 minus 128x. Ooh, this is awful. Okay, and this all equals 0. A little worried that there was a mistake made here somewhere. This is looking pretty bad, but let's just keep going. Let's just collect everything. So 2x, and we're going to get x to the 4th minus 32x cubed. What's the squareds? We have plus 256 minus 128, so plus 128x squared. And then what's with the x's? We have minus 2048 and then minus another 128, so that's minus 2176x. And then plus 4096 plus 1024 is going to be plus 5120, right, equals 0. Okay. All right, so I apologize for how terrible this algebra became, but we finally actually have an equation here that we can solve, although I don't know how to solve this by hand, so I'm going to have to solve this on the computer. Okay, so I'm going to have to solve this on the computer. So here we have x equals 0 as a solution. This is going to be a kind of ridiculous solution. And then let me just solve the other thing on the computer. So solve x to the 4th minus 32x cubed plus 128x squared minus 2176x plus 5120 equals 0. Yes.
That was?
Yes. Did I make a mistake somewhere?
Yeah, you mean you're gonna solve it using computer?
Yeah, I'm just going to type into Google, solve this equation.
Okay, because
Yeah.
if you solve the problem, you are expected to get probably like fourth root because if you have the four different value, four different s values.
Yeah, I mean, but there may only be one that's real, right?
Yeah,
So I don't know what the actual real solutions are. So I'm gonna put it into, I'm gonna go to Wolfram Alpha, where it's gonna, I'm just gonna say solve this equation, x to the fourth minus 32x cubed plus 128x squared minus 2176x plus 5120 equals 0. And when I solve this, okay, it gives me two solutions. Okay, so the solutions that it gives me is two real solutions. So x is equal to about 2.5, and it also gives me x equal to about 30. Okay, so 2.5 and 30 um, are the solutions. Okay, so let's look at our.
that
Sorry, yep,
was
yep.
yeah. You use Wolfram Alpha to solve it.
Yeah, Wolfram. Yeah, so this is Wolfram.
Yeah. I think the answer should have been like plus or minus 2.5 and plus or minus 30. Is not it?
No. It's only the positive ones because the other two solutions are imaginary.
Okay.
Yeah. Um, so those are
But,
the only real
but
solutions. Yeah.
so that Obus,
Yes, Princeton.
you said we have two answer. One more about the one that S should be equal to 0. So it's
Okay, so
not
that's a
valuable.
third solution also. So we have these three possible solutions,
Three
right?
answer
So
here.
0 and 2.5 and 30. And so again, I
Yeah.
apologize for how awful the algebra became here. I think we could try doing it in terms of trig, maybe not together, maybe as a homework problem, but that might make it a little easier. You do the whole thing in terms of trig instead. But since we have this, let's look back at our diagram. So what does it mean? X equals 0, x equals 2.5, x equals 30. Well, x equals 0 makes no sense, right? Because x equals 0 would mean the ladder, x equals 0 means the ladder hits the ground here, right? So x equals 0 would be something like this. It's not a solution that makes any sense, right? X equals 0 would be that the ladder is going down from here and up forever. That doesn't make any sense. X equals 2.5 would mean that it's part of the way up the wall, but not even as high up as the fence. So again, you would get something that doesn't make any sense. Right? So the only solution that makes any sense would be x equals 30, where you then are getting a ladder that's actually going down like this. Right? So for x equals 2.5 or x equals 0, the ladder doesn't even point the right way, right? Because it has to go through this point. It has to go over the fence. So x equals 0, x equals 30, totally extraneous solutions. Okay? Sorry, x equals 0, x equals 2.5 are totally extraneous solutions. Okay? Whereas x equals 30 is actually
that
a
over.
solution that makes some sense. Yes, Robert?
So 0 and 2.5, they are less than 8. That is the reason why we're going to take them into consideration, right?
Exactly, right? Since they're less than 8, and if that means a ladder that would hit the building at 0 or 2.5 is actually not going to hit the ground at all over here. So they can't be meaningful solutions. So the only meaningful one is the number that's bigger than 8. Exactly. It has to be bigger than 8 to be meaningful. Okay. So remember, it says, what is the length of the shortest ladder that will reach the ground over the fence? So we've solved that x equals 30. So I'm going to write x equals 0 and x equals 2.5. These two solutions are what's called extraneous. It means that you can't use them. Hey, we can't use them. Okay. Okay, but what about x equals 30? That's okay. And so now we need to figure out what the actual length is. So we have to go back and remember, what is our expression for the length? Well, the square of the length is equal to this, which means the length is equal to the square root of this, right? So the length is equal to the square root of this expression. Okay, so let me write that down. So let me get another page. Right, so recall that the length of the ladder, L squared, was equal to x squared plus 16x squared divided by x squared minus 16x plus 64. Okay, this was our length squared. So that means that the length itself is going to be the square root of this, the square root of x squared plus 16x squared divided by x squared minus 16x plus 64. Okay. And now what we're going to do is we're going to plug in x equals 30. I think the actual solution is 29.961, but we'll round it to 30. Okay. So what do we get when we plug in 30? We get that L, the length of the ladder, is the square root of 30 squared plus 16 times 30 squared divided by 30 squared minus 16 times 30 plus 64. That's equal to the square root of 900 plus 16 times 900 is going to be 14,400 divided by 900 minus 480 plus 64, or this is the square root of 900 plus 14,400 divided by, so 900 minus 480 is 420 plus 64. This is going to be 484. And now I'll put this in the calculator. So if we have square root of 900 plus 14,400 divided by 484, that says it's going to be 30. Wait, really? I guess so. Yeah, okay. So this turns out to be 30.49 feet. Roughly, since we rounded to 30, I'm going to round this to 30.5 feet. Okay, so it turns out that this is actually the shortest ladder that you can use that's going to go over the wall there. Okay, and the ladder at 30.5 feet, we can even think about this kind of geometrically what that means. It means that if you go 30 feet up the building, have to hope the building is actually 30 feet tall. If you go 30 feet up the building, then the length of the ladder, that's so high up that the ladder is almost going to be straight up and down. It only has to go a little bit outward in order to go over the fence. And so that means that the length of the ladder is 30 and a half feet. It's not that much longer than the height of the building, the height that you want it to reach on the building. Okay. So yeah, so that is what we have for this problem. So very involved, a lot of algebra, but really I want to think that this can be broken up into just a few steps. We first have an expression for what we want to minimize. This length, okay. All right, thank you, Abraham. We're 3/4 of the way through class anyway, so you've gotten to most of it. Okay. Okay, so we have this expression we want to minimize, x squared plus 4 plus y squared. We needed to write y in terms of x. To do that, we used either similar triangles or trigonometry, however you want to call it. And once we wrote this expression in terms of x, we had to take the derivative and set it equal to 0. Okay? And there's what we have. Okay? So yeah, and so this is how we do it. My guess is actually you're probably right. It would have probably been easier to just do this in terms of trigonometry directly from the beginning. So maybe we'll go over that version next time. Okay, so maybe we can go over that version next time. Okay. All right. Any questions on this so far? Okay, so setting this derivative equal to 0 again was some annoying algebra. Okay, so the answer doesn't come out quite as nicely as the previous one, but in the end you can solve it, and it turns out to be 30 feet. Okay. So if that's okay, all right. So let's move on to what we're going to do this today, which, we're not going to get as far because these problems took a long time, but it was worth it because I think these are good problems to practice. Okay, so we'll probably only get through the first derivative test today. Okay, so our new unit today is, what do derivatives say about graphs? Okay, so the first question is, suppose f of x is a differentiable function, and we look at the graph of y equals f of x. And so remember that at any value x equals a, the slope of the tangent line is f prime of a, right? This is what the derivative means. It gives you the slope of the tangent line. And so what does it mean if this derivative is positive or negative or 0, right? Well, in order to see that, we'll consider a basic example. Let's look at f of x equals x squared, right? So we all know what the graph of f of x equals x squared looks like. It looks like a parabola. Okay, so this is our parabola. Okay, so now we also know how to do the derivative. We have that f prime of x is equal to 2x. Okay, so what happens when we do f prime of x equals 2x? What does that mean? Well, let's notice that if x is greater than 0, then f prime of x, which is equal to 2x, is also greater than 0. And if x is less than 0, then f prime of x, which is equal to 2x, is also less than 0. Okay, so we see that for positive values of x, x-axis, my y-axis. So for positive values of x, we have that this derivative is positive, and for negative values of x, we have that this derivative is negative. And this is reflected in the slopes of the tangent lines, right? For positive values of x, we have a positive slope of the tangent line, and for negative values of x, we have a negative slope of the tangent line, right? And another way of saying that, when the slope of the tangent line is positive, is that that's saying that the function is increasing, right? When we have a positive slope of the tangent line, that means the function is increasing. It means it's getting bigger as x gets bigger. And when we have a negative slope of the tangent line, that means the function is decreasing. It means the function is getting smaller as x gets bigger. Okay, so what this says, what we can see here is that f prime of x being greater than 0 implies that the function is increasing. And f prime of x less than 0 implies that the function is decreasing. Right. F prime of x is greater than 0 means the function is increasing. F prime of x is less than 0 means the function is decreasing. Okay. Okay. And this is what we see with the parabola. If we go from left to right, it decreases down to 0, and then it increases as we go up from 0. And where it's equal to 0 right here, this is the critical point. This is the local minimum. Right, this over here is the local minimum. Okay. Questions?
Yeah.
Yes. Good.
Yeah, Marcus.
Yes. Marcus, yes, hi.
Yeah. So for the another name for a plan of x or plan of maybe y, it is also known as function, right?
Yeah, functions. Yeah. Yeah, there's
Okay.
f of x here is a function.
All right.
Okay.
Yeah,
You're
but
mute.
Alexander?
yeah,
Hello? Yes.
you know,
Hi.
is f prime or f cannot be the function as you're talking to. S prime of f is a derivative. I don't know
Right.
whether
So
I'm correct or
f of
not,
x
but
here is x squared and f prime of x is 2x. But we also, sorry, when I say function, sorry, let me be more clear. Sorry.
yeah, yeah.
Right. Okay. Thank you. So if f prime of x is greater than 0, that means that the original function, f of x, is increasing. And if f prime of x is less than 0, this means the original function, f of x, is decreasing.
Thank you, Dad. Then another thing, the local minimum, the critical point in that of relating it to the local minimum, I got lost between there. So
Yes.
please, Dad,
Yes.
provide some
The
clarity.
critical point here is a local minimum just from looking at the graph.
That's x increasing and f of s decreasing.
Yeah. Right. So f of x is decreasing when x is negative, and it's increasing when x is positive because of the derivative is 2x. So that's going to be negative when x is less than 0 and positive when x is greater than 0. Exactly. So exactly as James says here in the chat.
Okay. Thank you.
Great. You're welcome. Okay. So let's do a slightly more complicated example. Let's look at f of x equals sine of x. So I'm not going to draw the entire graph, but I'll just draw a little part of it. Maybe actually I'll only draw a part of it on the to the right of the x-axis. So let me do this. Draw f of x equals sine of x. Let me just label pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so we draw the graph of y equals sine of x. It looks like this. It's a sine wave, remember? This, whereas this up here is 1, and this down here is minus 1. This is as far as it goes. This is the graph of y equals sine of x. Okay. Okay, and we've seen that it has these local maxima and local minima where it's equal to 1. So sine of pi over 2 is equal to 1, and sine of 3 pi over 2 is minus 1. And we see that we have these horizontal tangents at these points. Horizontal tangent and horizontal tangent, right? So now recall that the derivative of sine of x, f prime of x, we calculated this last semester, it's equal to cosine of x. Okay. So remember, this is equal to cosine of x. Okay. And so what happens if I draw the graph of cosine of x? I'm going to draw the graph of cosine of x on parallel axes. Okay, so I'm going to try to put the x values in the same place. So this is pi over 2, this is pi, this is 3 pi over 2, and this is 2 pi. And if you remember, the graph of cosine of x looks like this. It starts at 1, it goes down to pi over 2, and then down, hits its bottom. Oh no, that's not what I want. Down to pi over 2, it hits the bottom at pi, goes back up through 3 pi over 2, and then gets to 1 here. Let me draw this part a little better. Goes up to 3 pi over 2, and then goes up to 1 over here at 2 pi. Okay, so here we have 1, and here we have minus 1. Now look at what's happening here with sine, right? So sine here is increasing. It's going, oops, it's increasing. It's going up from 0 to 1. Then on this entire interval over here, it's decreasing, right? Because it's going from 1 down to minus 1. And then on this interval over here, it's increasing again, right? So it goes increasing, then decreasing, then increasing. Okay? So what we've seen is that when it's increasing, it should have a positive derivative. That means the slope of the tangent line is positive. When it's decreasing, it should have a negative derivative. And when it's increasing again, it should have a positive derivative. And well, let's verify that, right? The derivative is cosine of x. So let's see. Well, cosine of x is positive here. exactly where sine of x is increasing, right? So sine of x is increasing. That means its derivative is positive. The derivative itself is decreasing, but it's still positive everywhere here. So cosine of x is positive. That means sine of x is increasing. Now between pi over 2 and 3 pi over 2, sine of x is decreasing that entire way. That means its derivative should be negative. And look, it is. The derivative of cosine of x is negative between pi over 2 and 3 pi over 2. And then lastly, from 3 pi over 2 up to 2 pi, sine of x is increasing again. That means its derivative should be positive. And when we look at it, it's exactly right that the derivative is which is this cosine of x here, is positive. So I'm going to write here it's positive, here it's negative, and here it's positive. And so I'm just going to observe what I just said. You know, f of x is increasing whenever f prime of x is positive. And likewise, f of x is decreasing whenever f prime of x is negative. Okay, so this works in general. We saw it with f of x equals x squared, and now we're seeing it also with f of x equals sine of x. Okay, when sine of x is increasing, that corresponds to cosine being positive, and when sine of x is decreasing, that corresponds to cosine being negative. Okay. All right, so, and this, of course, works for anything, but wanted to just, show it in this other example. All right, any questions about this example? Okay, everybody's phone starting to run low on current. We won't be doing that much more today. So certainly you're recorded for attendance, even if your phone ends up running low. Okay. So what do we see in general? This is actually a theorem which is called the first derivative test. So maybe actually before I state the theorem, I should notice that this here is a local maximum and this here is a local minimum. Okay. So what does the theorem say for the first derivative test? The theorem says that if I have a continuous function and I have a critical number, c, then if the derivative changes from positive to negative at c, then f has a local maximum. So let's look on our sine graph to see how that works. If the derivative goes from positive to negative, that's the same thing as the function going from increasing to decreasing. And that means you have a local max, right? Because the function goes from increasing and then it starts decreasing. So it gets to the top and then it starts decreasing. So if the derivative goes from positive to negative, that's the same as the function going from increasing to decreasing. That means that f has a local maximum at c. Okay? Similarly, if the derivative goes from negative to positive at c, then f has a local minimum at c, right? So if it goes from negative to positive, then you have a local minimum. And that's exactly what we have here as the local minimum, right? At the local minimum, this value 3 pi over 2, that's c, which is the local minimum. The derivative, which is down here, goes from negative up to positive, right? So I should say this here is, y equals cosine of x. Okay, so at the local minimum, the derivative goes from negative to positive. And then lastly, if f of x does not change sign at c, f prime of x does not change sign at c, so it's possible for the derivative to be 0, but for there not to be a sign change, then f does not have a local minimum or maximum at c. And so the most basic example of this would be if f of x is equal to x cubed, f prime of x is equal to 3x squared. Well, what happens here? If I graph f of x equals x cubed, it looks kind of like this. This is y equals x cubed. And the critical point, if we set, so the critical number is the solution to 3x squared equals 0, setting the derivative equal to 0, and that's the same thing as x equals 0. So this x here is a critical point, or a critical number, but it's neither a local minimum nor a local maximum, right? The function starts here increasing, and then it keeps on increasing, right? It's not a local minimum or a local maximum, and that's because this derivative doesn't go from negative to positive at x equals 0, right? What happens at x equals 0? Well, f of x equals 3x squared just looks like this, right? This would be y equals 3x squared, and at 0, it just goes from positive to still positive, right? Positive, it brushes 0, and then it stays positive, okay? So this example is where f prime of x does not change sign at c, right? In this case here, our critical point here is c equals 0. Okay, so on our earlier graph of sine x, we saw a local minimum and a local maximum. Depends on whether the first derivative goes from positive to negative or from negative to positive. And then for the for this example over here, the derivative does not change sign, which means that f does not have a local maximum or a minimum at c. Okay, because the derivative just stays positive, touches 0, and then goes back to being positive again. Okay, any questions on this?
All clear, all clear, all clear.
Great. Okay, so we only have 10 minutes left. So I guess, yeah, we can talk about the beginnings of concavity. What do I want to say? Yeah, okay. So we can talk about the beginnings of concavity, okay? So a section of the graph is called concave up or concave down as seen below. So what does concave up mean? Concave up means it looks like this or it looks like this. You should think of this as holds water, right? I mean, you can imagine water, it's kind of like a cup. Water can sit on top of this. This is what concave up looks like. And concave down looks like this. Okay, I think this is spills water. Okay, right? This, if you put water on top of it, it's just going to flow down. It's kind of like a top, right? So concave up, you should think of the graph could be like supporting things on top of it. Concave down means that the graph is kind of a roof on things below it. Okay, so this is what concave up and concave down mean. Okay, so notice that a section of concave up can be decreasing or it can be increasing, right? This section, this concave up curve is decreasing, but this concave up curve here is increasing. I'll write out the whole word. Decreasing and increasing, and similarly, this concave down here, this is increasing, but this one over here is decreasing. Okay, so concave up and concave down are independent of increasing and decreasing. You can have any combination of the two. You can be concave up and decreasing, be concave down and increasing, concave up and increasing, whatever you want, right? But basically, the sections of the graph look roughly like these four curves. You have concave up decreasing, concave up increasing, concave down increasing, concave down decreasing. Okay. All right. So how do we see this? Well, what does the second derivative of f say about its graph? So remember that the second derivative of a function is the function you get when you take its derivative twice. And so, well, what happens is that f double prime, what is that? That's f prime prime. That's right. You take the derivative and you take it again. And what we see is that, what does it mean that f double prime is positive? that means that the derivative of f prime is positive. And if the derivative of f prime is positive, that means that f prime is increasing. Let me write this out in a little more detail. F double prime greater than 0 means that f prime prime is f prime means that f prime prime is greater than 0, which means that f prime is increasing. Okay? And ditto, f double prime less than 0 means that f prime prime is less than 0 because they're the same thing, which means that f prime is decreasing. Okay? So the last thing that we're going to do, let's look at, oh, sorry, I'm getting echo. Okay, so let's look at these four curves. What's happening on these four curves? Okay, so we've got four different possibilities. So I've got my concave up here, my concave up over here, concave down here, and my concave down over here. Let's call these possibilities A, B, C, and D. So the question is, what's happening to the derivative here? Is the derivative, and all of these are going to be graphs y equals f of x. So y equals f of x, y equals f of x, y equals f of x, and y equals f of x. Okay. Okay. So what's happening here with the slope of the tangent line? With this one, we start with a very negative slope over here, and then as we move on, the slope is less negative, right? So we move on, the slope is less negative. So the slope goes from very negative to less and less negative. So what that's actually telling us is that f prime here is increasing, right? Because it's going from a very negative number, a steep negative slope, to a less negative slope. So you go from a big negative number to a small negative number, that's actually increasing, right? Similar here, we start here with a very shallow positive slope, and then we end up moving on to a steeper positive slope. So we're going from a small slope of the tangent line to a big slope of the tangent line. That means that f prime is increasing, right? Goes from a shallow slope to a steep slope. So over here, we also have that f prime is increasing, right? So f prime is increasing on both of these. What about C? Well, we start with a very positive slope, very steep slope. And then we end up over here, we go towards a shallower slope. So we're going from a big slope to a small slope. That means that f prime is going to be decreasing. Right? Because it goes from a high number representing the steep slope to a lower number representing the shallower slope. And then lastly, here we start with a small negative slope and we move on to a big negative slope. So it means the slope's getting more negative. And so that means here that f prime is decreasing. Okay? So what we see here is that for concave up, so remember what f prime increasing means. This means that f double prime is greater than 0. This means that f double prime is greater than 0. This means that f double prime is less than 0. And this means that f double prime is less than 0. So in the first case, for both A and B, we see that, concave up concave up means that f double prime is greater than 0. And in both C and D, we see that concave down means that f double prime is less than 0. Okay? And so this is the meaning of concavity. Okay, this is the meaning of the second derivative. Just like we saw that the first derivative tells you whether a function is increasing or decreasing. If the first derivative is positive, it's increasing. If it's negative, it's decreasing. Similarly, the second derivative tells you whether a function is concave up or concave down. Okay, so in this case, the second derivative is positive. That means the function is concave up. And here the second derivative is negative, which means that the function is concave down. So I'm just going to add it as an extra slide here, and then we'll stop. So I'll just say the upshot is if, what am I doing? If f double prime of x is greater than 0 on an interval, then f of x is concave up on that interval. And then likewise, if f double prime of x is less than 0 on an interval, then f of x is concave down. On that interval. Okay. So I think we'll actually stop there because we're out of time. I had some more problems and some examples I wanted to do, but we're going to hold those off until next week. So let me just skip these couple of pages. Second derivative test. Okay, so I'll give you these homework exercises and maybe omit 2 for now. We'll talk about 2 later on. Yeah, let's actually omit 2 and 3 for now. So I'll just say for the purposes of number 1, I'll just say an inflection point. I didn't define an inflection point. An inflection point means that f double prime of x is equal to 0. Okay, so it's kind of like a critical point, but for the second derivative. It's where you change from being concave up to concave down. So you can do problem number 1, and maybe problem number 2 is going to be try to redo the latter problem in terms of trigonometry. So what I mean by that is let theta be your variable. Okay, redo the latter problem in terms of trigonometry. Okay. All right. So this thing is for this function, find all the critical points and the inflection points, classify them into local maxima, local minima, and neither. And I'm asking you on what intervals is the function increasing, decreasing, concave down, or concave up. Okay. And then this second problem is going to be to redo this latter problem. Okay, so we mostly did optimization today, but we did a little introduction to what are the meanings visually of the first and second derivatives. Okay, so next week, February 7th, it's not February 7th, sorry, it's February 6th next week. We will finish the unit on curve sketching, and then we'll also proceed to discuss the chain rule for derivatives. So that'll be a little bit more computational after we finish the graphical stuff. Okay, so let's stop here. I think we've had enough for today. Okay, so thanks, and any questions? And remember to write your name.
Thank you, Duda.
All right. You're welcome.
All
All right, you're welcome. Thanks for your input. Thanks, Marcus. Benson, I want to make sure you got your name in here. If you didn't, I'll type it in. I don't think I saw it, so let me type it in myself. All right. Okay. So enjoy your weekend, everybody, and I will talk to you next week. Let me stop the recording.